So specific heat capacity of a substance is the amount of heat that has to be provided to a substance to raise its temperature by 1 degree centigrade. And how much of substance, let's say 1 kg of a substance. This I need to move down here at least. Okay, let it go over here. So if you need to take that down, let's write specific heat capacity of a substance of a substance is the heat required is the heat required to raise to raise temperature by 1 degree centigrade of 1 kg of a substance. Alright. So if you've got 1 kg of iron, it would require a different amount of heat to raise its temperature by 1 degree centigrade. If you've got 1 kg of water, 1 kg of mercury, 1 kg of gold, 1 kg of hydrogen, for any given substance, for 1 kg of its mass, the amount of heat which is required to raise the temperature by 1 degree centigrade. Current temperature is 5, you want to raise it to 6, it's 6, you want to raise it to 7 or whatever. So that is called specific heat capacity. Specific heat capacity. And so it is given by an equation. Q is equal to it's called this thing, the next thing is called heat equation. Let me write that. So we have got heat equation. Heat equation is Q is equal to m c delta theta or delta t. Okay, where m is delta theta. Where m is q is equal to heat energy. M is equal to mass of substance. C is equal to specific heat capacity. And delta theta is equal to change in temperature. Okay, a similar concept is the that of thermal capacity. So thermal capacity is thermal capacity is the yeah, you have written this down, right? Heat equation and all its
Yeah.
values. Okay, so thermal capacity, in fact, let's write it. Okay, let's continue writing over here. It's the amount of heat needed to raise the temperature of the whole body by 1 degree centigrade. So, mm, regardless of mass, for heat capacity, it was just for 1 kg of mass. Thermal capacity is, let's say, heat capacity regardless of mass. So, thermal capacity of a body, thermal capacity of a body is the amount of heat needed to raise temperature of a body by 1 degree centigrade. Okay, so if we again look at the previous equation, the heat equation that we wrote, Q is equal to mc delta theta. So if we are calculating the heat capacity, this m will be 1 and delta theta will be 1, right, for specific heat capacity. Since specific heat capacity is for 1 kg of mass and it creates a temperature change of 1, so we will get Q is equal to C.
Okay.
Okay, and here for thermal capacity, we are saying that we'll use the same heat equation, but now we will have mass of the body times specific heat times just 1, because change in temperature is 1. This would be
Mm.
thermal capacity. Okay, what would be the unit? The unit will be joules. Energy is given in joules. So for specific heat capacity, if I rearrange this equation, C will be equal to Q divided by M divided by delta theta. So it will be joules per kilogram per degree centigrade.
Okay.
For specific heat capacity, the unit would be joules per kilogram per degree centigrade. Okay, this, then anything else? Anything else? Okay, a substance with high specific heat capacity. For example, what do you think the specific heat capacity of water, is it high or low?
Low.
What would low mean? That it easily changes temperature, or it takes a lot of time to change temperature?
That easily.
Yes. And would it be lower than that of what that of iron or steel? The specific heat capacity
Mm.
of water, or higher than that?
No. It would be water would be lower.
For water, it's higher.
Really?
Yes. The reason is that if you have a, let's say, a pan made of steel and you put water in it and you start providing heat to it, the pan will become heated very quickly, whereas water would take some time to get heat up.
Mm.
All
Yeah.
right, and this property of water, it helps water act as a coolant, that it absorbs a lot of heat, yet it does not change its temperature quickly. So this property, it comes in handy then. Uh,
So is it lower? It's high. Water has a high heat capacity.
Water has a high heat capacity, meaning thereby that it needs a lot of heat to raise its temperature by 1 degree centigrade. So temperature of water you have to give, for example, the same amount of heat had you given to iron, it would have raised its temperature by, let's say, a few more degrees centigrade.
But it would have changed, like It would go. It would have gotten hot.
Uh, again, same heat given to water and to steel would raise temperature of steel more as compared to water.
Okay.
Okay. If you could please attempt these questions. Just a second. Hmm. Question 1 to 3, please.
$15,000 joules.
Yes, 15,000 joules per kilogram per degree centigrade. No, 15,000 joules. Just it's asking for heat. Thermal capacity. You have to give thermal capacity. 15,000 joules is what?
So it is 15,000 or no?
Mm, 15,000 joules is correct. How much heat is needed? MC delta T. 15,000 joules is correct. No, these are two questions in fact. So for the first one, how much heat is needed? It's correct. But what about what is the thermal capacity of the substance?
Mm,
Q is equal to MC.
Wait, I'm not sure about this one.
See, the formula for thermal capacity is mass times specific heat.
Hmm.
So simply 5 into 300.
So 1,500.
Yes, 1500. And for the first one, since it was heat energy, there are a few things involved over here, so I want you to be clear on all these different things. First is heat energy. If you calculate heat energy of any substance, the answer would be in joules. Okay. The next thing is a specific amount of heat energy. So that specific amount of heat energy is the heat energy required to raise temperature of a body 1 kg of body by 1 degree centigrade. That is specific heat capacity. If you calculate specific heat capacity, the answer is in joules per kilogram per degree centigrade. Are you following me?
Yeah.
The third thing is thermal capacity. Thermal capacity is simply raising temperature, how much heat is required to raise temperature of a body by 1 degree centigrade. So that is joules per degree centigrade. So three things: heat, specific heat capacity, and thermal capacity.
Okay.
Heat energy is any amount of heat energy ever given to anything. Thermal capacity is heat energy given to raise temperature of a body by 1 degree centigrade, and specific heat capacity is heat required to raise temperature of a body by 1 degree centigrade, but not any body, 1 kg of a body. All right.
Hmm.
So for heat energy, the answer was 15,000 joules, and for specific heat, the answer is 1500 joules per degree centigrade.
Yeah.
All right. Question two, please.
I think the whole screen just lagged out.
You can't see my screen?
No.
One second. You're solving question 2, right?
Yeah. So the formula was MC delta T.
Yes. What quantity do you have to calculate in this one, in this question 2?
Mm, joules.
Mm-hmm. So see,
Kilojoules.
no, no, let's see. Joules and kilojoules are units. So we have got this equation Q is equal to mc delta T. Q is heat energy,
Mm,
m is mass of the body, C is specific heat, and T is temperature or change in temperature, right?
mm,
So in this question, you are given heat, Q is given, see here, heat given, how much heat you give is given. So you can't be calculating, you can't be required to calculate Q in this one. Masses are also given, so different masses 1, 2, and 0.5, right?
yeah.
Okay, and then delta T change in temperature is also given 1, 5, and 4. So the only quantity that's left is C. Also here it says calculate the specific heat capacities of A, B, and C. So you have to calculate C, which is specific heat capacity, right? So in order to calculate specific heat capacity, I'll need to rearrange this equation. How? So I am told Q is equal to mc delta T. So to calculate C, it will become Q divided by m times delta T is equal to C, right?
Yeah.
And again, to contextualize, what does this C means? This means this is the amount of heat. So these are three different substances given, A, B, and C. And for each substance, a separate mass is given 1, 2, and 0.5. So when I calculate C, it tells me this is the amount of heat energy that I have to give to, for example, first for substance A, then for substance B, and then for substance C. This is the amount of heat energy that I have to give to this particular substance so that 1 kg of this substance, it raises its temperature raises by 1 degree centigrade.
Okay.
Total heat energy given for to any substance which would raise uh, its temp which would raise the temperature of 1 kg of its mass by 1 degree centigrade. Okay,
Okay.
so this is what we have to calculate over here. Now please go ahead, question 2.
Wait, can you go back 1 second?
Sure,
I
sure.
didn't write this one part down.
So I've simply divided both sides with m delta T.
Wait, can you go back to the question now? Wait, I still don't. I don't understand what my answer is gonna be.
Hmm. Let's see. For this question, I have to calculate C for, and I'm given three different materials. I am given material A. Let's do it for material A first. So in order to calculate C, I need to have Q. What's Q? How much heat is given to this material A? 2000 joules. So I write
Hmm.
C is equal to 2000 divided by what's mass of this material A given? 1 kg. 1 multiply by what's change in temperature given? Temperature rises by 1 degree centigrade. So it's 1. So C will come out as 2000 joules per kilogram per degree centigrade. Alright.
Yeah.
Okay. Then for next substance, same formula, C is equal to Q by M times delta T. So I again write C is equal to heat given to this second substance is also same. So we are giving same 2000 joules to different substances, but each time substance is different and mass is different. So M for substance 2 is 2 kg. So this will be 2, and delta T temperature rises by 5 degrees centigrade. So multiply by 5. So 2000 divided by 10 will be 200,
Hmm.
200 joules per kilogram degree centigrade. Alright,
Yeah.
the same way for the third one. So for third one also it will be C is equal to 2000. Mass for third substance is 0.5 and its temperature rises by 4. So 0.5 into 4 is 2. 2000 divided by 2 is 1000 joules per kilogram per degree centigrade.
Okay.
So the first one was for substance A, this was for substance B, and this was for substance C. Hmm. Can you attempt it now?
Can you go back?
Hmm. I just don't want you to copy the solution. I mean, it's there. You can see it as many times as you wish to, but you must understand it's simply rearrangement of the formula. Even if you do not understand the concept, you have to calculate the value of C. Equation is
Okay.
Q is equal to MC delta T. So C can be calculated by Q over M times delta T. Did you get how you get this equation from the original one?
Yeah, because you rearranged the formula.
I rearrange the formula, and then it's just a matter of putting in the values Q, M, and delta T.
Hmm.
Shall I switch back to question?
Yeah. So when I rearrange this now, I would do 2000 over 10.
Mm, 2000 over 10 for substance B?
Yeah.
Yes, it would be 2000 over 2 into 5.
Mm-hmm. And then for C it would be over
0.5 into 4,
2.
which would be 2.
So yeah, okay. So B would be 200 and C would be 1000.
1000. Perfect. Perfect. The last one?
Because it has a lower heat capacity.
Mm, so specific heat capacity of jam is higher than that of pastry so that it cools more slowly.
Hmm.
Mm, okay. The next thing that we have is specific latent heat. Okay, so when I am heating a solid, I know that solids upon heating they liquefy. Alright, this is called fusion. The thing is that if I draw a graph, so here I've got hmm, on x-axis, let's put heat, and on y-axis, or let's say I'm applying a constant heat to this particular substance. On x-axis I've got time, and y-axis I've got temperature. Okay. Uh, mm, 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 mm. Hmm. So a liquid which is cooled down to solidify as time passes by, it loses heat until it reaches a certain temperature. Then for some time the temperature becomes constant and then it starts dropping again. Okay.
Mm.
Similarly, if I'm applying constant heat to a solid so that I may liquefy it, time and temperature. So as time passes, the temperature it increases. It reaches a certain point where it becomes constant and then it liquefies and then the temperature rises again. So what is happening over here is that we know that we have studied the kinetic molecular theory for solids, liquid and gases. When we have got a solid and we are heating that solid, initially when we provide heat to the solid, the temperature would rise. And the temperature rises because the molecules of the solid they are vibrating more vigorously. All right. So they would keep on vibrating. And when I keep on adding the heat that I provide to those molecules, a point would come when the intermolecular forces would break down. Okay. So a point would come at this particular point, at this particular point of time, the heat that I am giving to this substance is no longer increasing the temperature of the substance, rather, it is breaking the intermolecular forces between the molecules. Are you following me?
Yeah.
And then, once they have been broken at this particular time, it would have become liquid, and here onwards, the temperature it would start rising for liquid again. This amount of heat which I have to give to a substance so that its temperature does not change, its temperature remains constant. However, the state of the matter changes. This is called latent heat of fusion. This is called latent heat of fusion. Let me write down the exact definition as well. You can note that down and then we'll see questions after that. So, we have got specific latent heat of fusion of a substance is the quantity of heat needed to change unit mass from solid to liquid without temperature change. Equation would be Q is equal to mass times latent heat of fusion. and unit would be joules per kg. If I rearrange it, it will become latent heat of fusion is equal to Q over M. So unit is joules per kg. So the same way we have specific latent heat of fusion, we also have specific latent heat of vaporization. Hopefully you've got this concept of specific latent heat of fusion, right?
Yeah.
So specific latent heat of vaporization, can you tell me what would it be?
Can you repeat the question?
I've given you specific latent heat of fusion, and it
Mm.
is for the amount of heat which I've given to a particular solid so that it changes its state without raising the temperature. So what would be
Yeah.
specific latent heat of vaporization?
So the energy needed to change
Hmm.
1 kg of the substance without changing the temperature?
1 kg of substance from what to what? From liquid to vapor.
Oh, yeah, because vaporizing, yeah.
Okay, for that, for fusion it was for solid to liquid. Now for vaporization it would be from liquid to vapor. So vaporization of a substance is the quantity of heat needed. Any tests coming up?
Not yet, no.
Do you have anything like monthly or weekly tests at your school?
Whenever we finish a unit, they do a test.
Mhm. So last test was on unit of heat
It was on the V equals to IR one.
or electricity.
Mm.
So which topics are you covering at school these days then?
So we're doing the electricity one right now.
Okay, so you're
I
still
mean, we
continuing.
finished. Wait, so right now, because I have holidays,
Hmm.
we're gonna start school on Sunday.
Hmm. Mm-hmm. Mm-hmm. It was like a week of holidays.
Yeah. So, like, like how electrons move and stuff,
There is a
and
topic of radioactivity.
parallel and
Hmm.
series.
Hmm. Hmm. All right. All right. Uh, After that, you have a topic of radioactivity, which is common between physics and chemistry. So you'd study the same thing for both. I don't know if you've got the same teacher or different teacher at school for both subjects, but that topic
Different.
is common. Hmm.
All subjects have different teachers.
Mm-hmm. What about other subjects?
Uh, what about them? Like test wise?
Topics that you're doing these days. I mean, the last topics that you have covered.
So math, we're like pretty behind, I'd say, because
Hmm.
we're doing trigonometry right now.
You're done with gradients, the straight line equations.
What chapter is that again?
I mean, varies from book to book. Did you do y is equal to mx plus c? or
No, not yet.
y2 minus y1 is equal to m times x minus x1. That is straight line
Mm.
equations.
The
Hmm.
graphs, we didn't do them yet. No, it's the next chapter.
Okay, and probability.
No, we haven't done that either.
The school usually finishes your syllabus by Feb end, roughly, right?
Yeah,
So that your CIs are in uh, April, mid-April,
May,
end of.
June.
Hmm,
Well, let's say like I do French and like listening for French is
hmm,
in and April, and the
hmm,
ICT tests are also end April, but I don't do ICT.
hmm, 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 hmm. So for your subjects, they'd be in May and June.
Yeah.
Mhm.
Biology, we're like about to finish. We're doing plant reproduction right now in biology.
Plant
Chem-
reproduction.
yeah.
Hmm. And
In
hmm,
chemistry, we've just finished metals,
hmm,
and on Sunday there's going to be a test from everything we did, including last year's work.
hmm, hmm. So metals, when you study metals, do you study bonds in chapter of metals, or is there a separate chapter on atomic bonds, the covalent bond,
Uh,
metallic bond, ionic bonds,
yeah,
those
that's
things?
a separate chapter. We did that like last year in the beginning.
Hmm. Hmm. So what did you study
For
in metals now then?
uh, like electrolysis, we did that as well.
Mm-hmm, mm-hmm, mm-hmm. Electrolysis is covered over here, all right.
Yeah.
Uh,
For what else? Business, we're doing marketing.
all right. So you must have completed HR, and you must have completed that organizational structure thing where you study about different types of businesses, uh,
Yeah.
limited companies, private limited companies,
Yeah,
corporates.
that was like last year.
Hmm. And HR is also finished. Have you done the chapters of finance yet? The financial
No.
statements and accounting ratios, those things you have not yet.
No, no.
Mm-hmm, mm-hmm. And what about production? That just in time and
Yeah, that's the one that we just did.
mm-hmm, mm-hmm,
The JIT and the Kaizen and batch production.
hmm, hmm, hmm. All right. International businesses, international trade. Have you done that? Not yet.
No.
Mm-hmm, mm-hmm. All right. Let me know when you've covered all of this.
Okay. Okay, I'm done.
Okay. The next topic is evaporation and boiling, but I'd rather we start that in the next class. It's almost time for my next class, and she has just texted me. Can we start this topic of evaporation and boiling in the next class?